Have you ever tried explaining the behavior of electrons in atoms using just classical physics? If you did, you'd quickly run into problems, especially with multi-electron atoms. Bohr's model, though revolutionary for its time, proposed fixed circular orbits for electrons but couldn't explain fine details like the splitting of spectral lines or the behavior of electrons in complex atoms. Electrons were observed to behave not just as particles but also as waves. This dual nature demanded a new theory, one that could incorporate both wave-like and particle-like behavior. That theory is quantum mechanics. In this new model, electrons are not said to revolve in orbits like planets around the Sun. Instead, they exist in regions of space known as orbitals, areas where there is a high probability of finding them. This new perspective helped explain phenomena that Bohr's model could not, and gave rise to a more accurate understanding of atomic structure, one that lies at the heart of everything from lasers to LEDs to the functioning of atoms in chemical reactions. Let's dive into the core of quantum mechanics, Schrödinger's wave equation. In its time-independent form, it is written as capital H followed by psi equals capital E followed by psi. Here, capital H stands for the Hamiltonian operator, which represents the total energy of the system, including both kinetic and potential energy. The symbol psi represents the wave function, and capital E stands for the energy of the electron. While psi itself does not have any physical meaning, the square of psi, written as psi raised to the power 2, gives the probability density, which tells us the likelihood of finding an electron in a particular region of space. When this equation is solved for hydrogen-like atoms, it yields a set of quantized energy levels and wave functions, which we interpret as orbitals. These orbitals have specific energies, shapes, and orientations. So instead of electrons traveling in perfect rings, we now understand them as cloud-like regions where electrons are most likely to be found, a concept made real by Schrödinger's powerful mathematical model. From Schrödinger's equation come 4 quantum numbers, unique identifiers for every electron in an atom. The first is the principal quantum number, written as small letter n. It indicates the main energy level or shell and takes values like 1, 2, 3, and so on. The second is the azimuthal quantum number, denoted by small letter l. It defines the shape of the orbital and ranges from 0 up to n-1. When L equals 0, the orbital is spherically shaped and called an s orbital. When L equals 1, it is called AP orbital and has a dumbbell shape. When L equals 2, it is AD orbital, and when L equals 3, it is an F orbital. Next is the magnetic quantum number, denoted by small letter m. It determines the orientation of the orbital in space and can have values ranging from negative L to positive L, including 0. No two electrons in an atom can have the same set of these 4 quantum numbers. That's the Pauli exclusion principle. So, what do these orbitals actually look like? The answer lies in the probability density derived from the square of the wave function, that is, psi squared. An s orbital, where L equals 0, is spherical. It's like a round cloud centered on the nucleus. It's the same in all directions. A p orbital, where L equals 1, looks like a dumbbell or 2 lobes on either side of the nucleus. These come in 3 types, px, py, and pz, depending on their orientation. A d orbital, where L equals 2, has more complex shapes, typically cloverleaf forms. These shapes aren't just for show. They determine how atoms bond, how molecules form shapes, and how chemical reactions occur. Each shape represents a solution to Schrödinger's equation, with real physical meaning. Orbitals don't show exact paths of electrons, but rather the areas where we're most likely to find them. And that's a huge leap from Bohr's fixed orbits, Now let's understand how likely we are to find an electron at a certain distance from the nucleus. This is where radial distribution curves come into play. The probability density, psi squared, gives us the likelihood of finding an electron at a point, but electrons move in 3 dimensions. So we multiply psi squared by the surface area of a spherical shell at a given radius to get the radial probability. This tells us the probability of finding an electron at a certain distance from the nucleus. For example, in a 1s orbital of a hydrogen atom, the maximum probability occurs at 0.53 angstroms. This is known as the Bohr radius. As we move to orbitals like 2s and 2p, we see more complex behaviors. There are peaks and nodes, places where the probability drops to 0. On the radial distribution graph, these peaks and nodes help visualize how the probability is spread out. And you can see that 2s orbitals, for instance, have a region near the nucleus with low probability, followed by a peak, something the Bohr model never accounted for. Let's now decode the concept of nodes. A node is a region in an orbital where the probability of finding an electron is 0. There are 2 types of nodes, radial and angular. Radial nodes are spherical surfaces within the orbital, and angular nodes are planes or cones depending on the orbital shape. The total number of nodes in an orbital is equal to n-1, where n is the principal quantum number. The number of radial nodes is given by n-l-1, where L is the azimuthal quantum number. For example, in a 2s orbital, n equals to an L equals 0, so there is 1 radial node. For a 2p orbital, where n equals to an L equals 1, the number of radial nodes is 0, but there is 1 angular node. These nodes directly affect the structure and energy of orbitals. In visual representations, nodes appear as gaps or regions where the electron cloud disappears, a concept that brings a new dimension to the behavior of subatomic particles. Let's wrap this up with a quick summary. The quantum mechanical model of the atom explains that electrons behave like standing waves and are described by wave functions, not precise orbits. Schrödinger's equation, spelled as capital H psi equals capital E psi, gives us those wave functions and the associated energy levels. From it, we derive quantum numbers: n for energy level, L for orbital shape, m for orientation, and s for spin. Orbitals are visualized as regions where electrons are most likely to be found. S orbitals are spherical, Pe orbitals are dumbbell-shaped, and d orbitals are more complex. The concept of probability density, radial distribution, and nodal structures helps explain electron distribution around the nucleus. These ideas revolutionized how we understand atomic structure, chemical bonding, and periodic properties. I hope you now appreciate how quantum mechanics transformed the way we see atoms, not as tiny solar systems, but as dynamic, probabilistic systems that govern everything from atomic spectra to semiconductor design. See you in the next session as we dive deeper into electron configurations and periodic behavior.